Astronomers have been shocked, and quite literally. The James Webb telescope has detected a black hole 70 million light-years away, whose shock waves of dust and gas are overturning our previous theories about the energy sources of active galactic nuclei. But what are some of the most powerful spectacles that have taken place in the depths of the universe? Why do they contradict our current models? And why could the mass monster, nevertheless, help us to solve one of the greatest mysteries of modern space research? They are considered to be cosmic omnivores, gigantic machines of destruction that wipe out everything that gets in their way. And yet, this is only half the truth about black holes. However, it is undisputed that the gravity monsters have the destructive property of irretrievably swallowing up everything that crosses their path due to their extreme compactness. But to understand what lies behind this often cited compactness, it is worth taking a look at the following example. The diameter of a hypothetical black hole with the mass of the Sun would be a whole 2.9 kilometers, and a black hole with the mass of the Earth would not even crack the 1 centimeter mark. As a result of the incomparably strong gravity that results from this, nothing that has passed the event horizon of a black hole can cross it again from the inside to the outside. No radiation, no information, and certainly no matter. But outside the cosmic death zone, and this is the decisive factor, the bizarre objects behave like all normal massive bodies and can be easily orbited by other celestial bodies on stable orbits. And although supermassive black holes, which can exceed the mass of the Sun by a factor of millions or even billions, still pose many great mysteries for researchers, they are believed to play a fundamental role in the evolution of galaxies. But that's not all. Astronomers now assume that almost every galactic center is adorned by a supermassive representative of these cosmic monsters, and the Milky Way is no exception. Our central black hole goes by the name of Sagittarius A star and has a good 4 million solar masses. The extraordinary black hole, which is currently dominating the astronomical headlines with its unexpected spectacles, lies dormant in a galaxy with the rather unwieldy designation ESO 428-G14, and it shows us once again how much we still have to find out about the processes in the universe in the future. How black holes satisfy their hunger. Quote, "There is much debate about how active galactic nuclei release energy into their surroundings. We would not have expected radio jets to cause such damage, and yet they do." The man who summed up this unexpected finding in his statement is David Rosario. The Newcastle University lecturer is a member of the Galactic Activity, Torus, and Outflow Survey, or GATO project for short. This research collaboration uses the James Webb telescope to study the nuclei of nearby galaxies and has recently made a groundbreaking discovery. As mentioned at the beginning, the Galaxy of Desire is located around 70 million light-years away from Earth, and it harbors an active supermassive black hole at its heart, which greedily consumes the matter around it and emits intense light across the entire electromagnetic spectrum. Against this backdrop, the giant can help itself to a rich galactic buffet that other black holes could only dream of. Let's take another look at Sagittarius A star. In fact, our black hole is surrounded by so little matter that it's the equivalent of a human eating a grain of rice every few million years. Due to the cosmic forced diet, Sagittarius A star is therefore considered a quiet black hole, but it has a number of noisy neighbors. These include, for example, the supermassive black hole M87 star, which sits enthroned in the center of the eponymous galaxy Messier 87. At a distance of around 55 million light-years, it's not only significantly more massive than Sagittarius A star, with 6.5 billion solar masses, it's also surrounded by a gigantic amount of gas and dust, which constantly supplies the structure with new material. Due to its angular momentum, however, the matter cannot simply fall directly onto the M87 star, but instead forms a swirling, flattened cloud of gas and dust, an accretion disk that gradually feeds the black hole inside. However, supermassive black holes, such as M87 star, do not have the property of simply waiting passively to be fed. Quite the opposite. The extreme gravitational force of the colossus generates enormous tidal forces in the accretion disk, which consequently heats up to 10 million degrees Celsius. the immense heat in turn causes the accretion disk to shine brightly, contributing to the luminous spectacle of the active galactic nucleus. How a shock makes astronomers rethink their approach. But no matter how voracious a black hole may be, the surrounding food does not end up completely in its maw. The strong magnetic fields direct some of the matter in the accretion disk towards the poles of the black hole, accelerating the charged particles to almost the speed of light. From the two poles of the mass monster, this matter is in turn hurled outwards in the form of parallel jets. Jets that are also accompanied by emissions throughout the electromagnetic spectrum, especially radio waves. As a result of all these factors, active galactic nuclei can be so bright that they outshine the light of all the stars in their home galaxy. But for all their radiant power, the pulsating hearts of galaxies were often invisible to telescopes in the past. This is because the dust that envelops the active galactic nuclei blocks our terrestrial view by absorbing visible light and other wavelengths of electromagnetic radiation. However, infrared light can pass through the veil of dust, and conveniently, the James Webb telescope was designed specifically for infrared astronomy. With this in mind, the most powerful space telescope of all time is the perfect key to opening the door to the hidden centers of active galactic nuclei. And when the Gato team turned that key in the galaxy ESO 428-G14, they found that the dust near the supermassive black hole spreads out along its jet. In the same breath, however, the researchers also identified an unexpected relationship between the jets and the dust, suggesting that the jets of energy emitted could be responsible for both heating and shaping the dust. In other words, the experts discovered that the energy that heats up this swirling cloud of gas and dust may actually come from collisions with gas jets, and not from the supermassive black hole itself as previously thought. The detection of such a shock structure came as a surprise to the scientists, to say the least, but it shows the enormous effects that the radio jets from black holes can have on their surroundings. The bottom line is that the dusty shock may also hold a much greater potential for knowledge. By studying the dust in the vicinity of supermassive black holes, experts could understand how galaxies recycle their material, and how exactly the gravity monsters influence galaxies in general. A central black hole rarely comes alone. From ESO 428-G14 back to the center of our Milky Way, the discovery of Sagittarius A star took place in February 1974, even though astronomers Bruce Bielek and Robert Hanbury Brown didn't actually know what they had found in the gigantic expanses of space. In fact, the experts only found an unnamed radio source in the constellation of Sagittarius, and it was only the series of observations over several years from the 1990s onwards that revealed this radio source to be a black hole. Now, however, it could be that the next cosmic revelation is imminent, because the latest data actually suggests that Sagittarius A star is not alone, but is accompanied by an extremely rare representative, a so-called intermediate black hole. In order to understand how such a giant can be detected, however, we must first remember that a black hole can only be detected via the gases orbiting its event horizon and its effect on nearby stars. The extreme gravity of the black hole accelerates the blazingly bright celestial bodies to record speeds and distorts their light. And strictly speaking, new stars should not even form in such extreme regions, as the gas clouds required for this would be torn apart in an instant. Well, that's what you would think at least. But in reality, the astronomers found not just one, but several protostars which, along with their dust cocoons, lie dormant in the immediate vicinity of Sagittarius A star. The bottom line is that the stellar babies are only 0.1 to 0.3 light-years away from the black hole. But how did they manage to defy the merciless conditions of their home? Well, this is precisely the question that the team led by Florian Peisker from the University of Cologne also addressed. The astronomers analyzed the motion data of the star cluster IRS-13, which is also home to the impossible protostars. And ultimately, IRS-13, as the densest and largest coherent structure in the immediate vicinity of Sagittarius A star, was to hold a big surprise for the experts. The investigation of around 50 stellar orbits revealed a new structure that initially left the researchers baffled. The scientists detected a disk-like system in the deeply embedded cluster, and they realized that the stars in this cluster follow orderly orbits that cannot be explained by the influence of Sagittarius A star alone. In the same breath, IRS-13 also turned out to be much larger than previously thought. But what exactly holds the cluster together and influences the orbits of its stars? To find out, the astronomers also relied on data from the ALMA Observatory and NASA's Chandra X-ray telescope. And lo and behold, the datasets showed that there is a zone in IRS-13 in which ionized gases orbit at high speed around an invisible center. According to Peisker, this suggests that a 30,000 solar mass intermediate black hole is hidden in the affected star cluster. This is a class of black holes that has hardly been researched to date and is considered a possible precursor to supermassive black holes. In the case of IRS-13, the theory now states that the gravitational effect of the intermediate black hole holds the stellar association together and at the same time acts as a stabilizing antipole to the gravitational pull of the significantly more massive black hole, Sagittarius A star. If the existence of Sagittarius A's stellar sibling is confirmed, space research would be enriched by an absolute sensation for two reasons. On the one hand, intermediate black holes are extremely rare. The known candidates to date can be counted on one hand. And on the other hand, they are considered a possible intermediate form between stellar black holes from supernovae and the supermassive formations in galaxy cores. And it could be that supermassive black holes result from the mergers of these intermediate forms. In other words, IRS-13 could harbor an essential building block for the growth of Sagittarius A star. And the experts are now planning to put their exciting hypothesis to the test in future observations. And you are now welcome to put your subscription status to the test. Feel free to click subscribe if you haven't already, and never miss another exciting video from us again.